This is my online notes for Engineering Electromagnetics, the 8th edition by William Hayt and John Buck. And we'll start out with Chapter 1, which talks about vector analysis. And the first thing that the author introduces is scalar, which is something that has magnitude only. And that would be like temperature or time or like mass. And then the other thing would be, or for electronics, I guess we could throw in current and voltage, or scalars. Resistance, the scalar, it only has a magnitude. And then the other thing is the vector, which has a direction. It has a magnitude and a direction. Stuff like the velocity and acceleration and say the electric field and the magnetic field and things like that. And he introduces three coordinate systems that are used throughout the book. You got rectangular, and then cylindrical, and then finally spherical. Where a rectangular is you have x, y, and z, and you have some unit vectors, ax, and this would be ay, and this is az. So I used a little line across anything that's a vector, or he uses kind of boldface in the book, but I'll just use line. And then in cylindrical system, I'll draw again the axis here, and I can draw a circle here. You have a row, and then you have basically this direction, a phi, and then you have the same az as you do in the other axis, az. And then in spherical, so we have some like spherical surface here, and you have a distance out, and so the unit vector is going to be AR, and then we still have the A phi vector, A phi, and then let's see, and then you would have something like an A phi. So A theta, whoops, this one should be A phi, and this is A theta. So in spherical system, you have your x, y, and z in rectangular, and then in cylindrical you have your rho, and you have your phi, and you have your z. And then in spherical you have r, theta, and phi are your coordinates. So we all know x, y, z is some point out here, and so in the cylindrical you have a distance rho from the axis. Basically phi is this distance, or this angle out from the x-axis, we could call it. And phi basically runs from 0 to 2 pi. And then you have z pointing up in the z direction. In this system, you have r going out to the surface of the sphere. And then you have, again, the phi, which goes from 0 to 2 pi, which is the how far r is away from the x-axis. And then you have down here, coming down, you have theta. So theta goes from 0 to pi, and it's from the z-axis. So phi starts at 0 and goes out from the x-axis, and theta goes down from the z-axis. That's page 1. And so you can have these differential lengths of, and say we'll do a rectangular again, rectangular. And so if you had a vector from the origin, it would have a differential length of dx ax plus dy ay plus dz az. And then for rectangular, or no, cylindrical, you have a dl is equal to d rho, a rho, plus rho d phi a phi plus dz az. And then in spherical, your differential length of, say, so again I have some vector that's going out from the origin, and a differential length would be represented by that. And then finally dl for spherical would be, so how I remembered is this is x, y, and z, so you can construct the dl from that. And this is rho phi z, so you can get there. And then in spherical, you're r theta phi. And so you're going to have dr ar plus r d theta a theta plus r sine theta d phi a phi. And I went through probably like 9 of the chapters of the book, and you really need to just memorize these 3 equations. So it'll make your life so much easier when you're working the problems. And you can get the differential surfaces, like say dx. It's just you look at the x component, and it doesn't have to do with anything of the x, and you just put the other 2 components on there. So we have dy, dz, ax. All I did was just take the coefficient of the y, coefficient of the z, and then, because surfaces, and this is something that you should remember throughout the book, and are always defined as outward normal. Okay, so if we have x, y, and z, the x surface is going to be along this direction. It's going to be this one that I've just put right there. And so this distance here is going to be dy, this is going to be dz, and it's going to be outward normal. So dy, dz, outward normal is ax. And likewise in the cylindrical system, if we pick, say, we wanted to know the phi surface, you would just pick the other 2 components, so that's d rho, dz, a phi. And in the spherical system, if you wanted to know, say, the r, and then that would be the other components, so that would be r squared sine of theta d theta d phi ar. So it's always the other two components tacked onto whatever you're looking for. So again, this would be, for this guy, it would be this component plus this component tacked onto this component. And also, because you've memorized these three lengths, you can also get the volume. So it's just going to be the differential volume is going to be dx, dy, dz. And the spherical, you just take the coefficients of the cylindrical component. So that's going to be rho, d rho, d phi, and dz. That's going to be dv. So right here, it's just the coefficients of those things. And likewise for the spherical system, it's going to be r squared sine theta, r squared sine theta, dr, d theta, d phi. And the volume is a scalar. So just remember that. Volume is a scalar, with the surfaces are vectors. And so that's why I say it's just best, because when you're working on the problems that I've worked through, you just remember these three lines here, the differential lengths, and you can, from that you get the surfaces and the volumes, and it just makes your life easier. And to get these, I just memorize what the coordinate systems are, and then I can usually just quickly get the dl. So the next thing they talk about, well, actually, they don't talk about the differential links in chapter 1. I found that actually in a later chapter, but it should have been in chapter 1. It just makes life so much easier if you just memorize that from the start. And so if we have a generalized vector in the, and again, I make vectors just with a little hat on the top, but some people may like to do it like this, or some people may like to do it like this. I just do it with the hat on the top, or with the line on the top and not the caret or the whatever else it is. It's just simpler to write. And so you have a coefficient to your unit vectors, by, then ay, and the coefficient is just some number, a scalar, tacked on to the unit vector. Oops, that should be in the z direction. And you can get the magnitude equal to the square root of bx squared, whoops, there's no vector sign there, plus by squared plus bz squared. And if you want the unit vector, it's just b divided by the magnitude of b, which I give right there. And then we can go into the dot product, and it's defined as the vector a dotted with vector v is equal to the magnitude of a plus the times the magnitude of b times the cosine of theta and the angle between them. And just some property of the dot product, a dot b is equal to b dot a. I think that's a commutative law of dot products. And the important thing here is remember that the cosine of 0 is equal to 1, and the cosine of 90 degrees is equal to 0. So that means if you have ax dotted with ax, that's equal to 1. And then likewise, ay dotted with ay is equal to 1, and az dotted with az is equal to 1. And anything that's not is going to be 0. So ay dotted with ax is going to be 0, because these are basically collinear, and so their angle's 0. So that means it's 1, and these are 90 degrees apart, so that's 0. So like a x dotted with a z would also be 0. And then if you just have two vectors, a and b, and you know their vector components, then you can write the dot product as just the components. And the dot product is a scalar. It doesn't give you the results as a scalar. It does not give you a vector back. So ay, by, plus az, bz. And so that's the vector component. And so you'll have to find this from what I've read many times is if you want to say the scalar component of A in the direction of B. So if you had two vectors and you want to spread the scalar component of A, so you say A, and you want the direction of B, not B, but the direction of B, so that's going to be the unit vector. So this gives you the direction of B, of B. And they say they want the scalar component, so that's all it is. And if you want the vector component of A in the direction of B, then that's going to be A dot AB, and so that'll give you the scalar component, and then you want in the direction, and so that'll be the vector component of A in the B. And so this would be something like this, where you had this angle theta, and this is A, and this is the unit vector. Well, this big vector we'll say is B, and this is the unit vector in the direction of B. Okay. Now, the next thing they define is the cross product. And that's defined as if you have two vectors, A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle between A and B times a unit vector. And the n means a unit vector normal to A and B. And if you want to find the direction of that unit vector, you could draw it out, okay? And we call this A, and let's say both of these are in the plane of the page. This is vector A, this is vector B. And so what we do is we screw A into B using a right-hand screw. And so we would screw it this way, and the screw would go into the page. So how I've drawn it, A sub n would be going back into the page like this, A sub n. And so the cross product gives you a vector back, because this is a vector back from the input. And if you know the components of the A and B, then you can calculate it by using this sort of the matrix determinant way of doing it. Let's write this again on a new page. So we have A cross B, and we're going to use the matrix way to do it. Let me change my pen here. Whoops. And so you write down the three components of a rectangular system, and this works also for the cylindrical and polar. And then you write the three components of your vector. And A in your vector B. So you had something like A is equal to AX plus AY plus AZ. And so you have BY and BZ. And then you just do the determinant. So AX cross, oops, I'm sorry, not A. The vector A crossed with vector B is going to be, so you just cross out the other two ones. So you go AY BZ minus AZ BY times AX. And then we go minus, and then we do the same thing for the middle one. AX BZ minus AZBX times AY plus AXBY minus AYBX times AZ. And so that's how you get the direction. So how you do that again is you just cross out these two lines. So I'm going to do here cross, cross, and then you would do this one, the product of this one, these two minus the product of that one. And that's how you get each component. And you may see that other people write this middle component as plus AZBX minus XBZAY. It's the same thing, we just move the minus sign out. And so you just keep how you do it consistent. And it's up to you however you want to do it. So the last thing here is when you're finding a component of, let's say you had a vector. And let's see, you had vector A. And it's equal to AX and plus AY plus AZ. Okay. And let's say you wanted to do a coordinate transformation, and you wanted to find, so this is rectangular. And let's say you wanted to find the cylindrical coordinates. And so what you do is you say a rho, because remember cylindrical is rho, phi, and z. A rho is going to be equal to A dotted with a rho. And likewise, a phi is going to, and this is the magnitude, because a dot product is only magnitude, A dotted with a phi. And likewise, a z is going to be A dotted with a z. So that would be the rectangular transformation. And so this is going to be equal to AX dot a rho plus AY dot a rho plus AZ dot a rho. Now at this point, you would look up on table 1.1. I haven't memorized these yet. And you would see that this and the values for these dot products are listed in that table. So you get, and if you're using that table, then x dot a rho is equal to cosine of phi, And then you have AY, and AY dotted with a rho is equal to the sine of phi. And then AZ, and AZ dotted with a rho is equal to 0. And so if you wanted to say the, if we're just fully converting it, the A rho component, if we want to say it's a vector now, okay, then we could say for the A rho, then we could say AX cosine phi plus AY sine phi times A phi. And then you do the same thing for the A, not rho, I mean whoops. I made a mistake here. I was switching my labels here. There's no theta in that coordinate system. And so you do the same thing with a phi and a z by looking at that table. And the author also presents the coordinate transformation. X is equal to rho cosine theta, y is equal to rho sine, whoops, no, I did it again. We're talking about phis here. Sine phi, and z is equal to z in the, if you're transforming. Let me see if that makes sense. We have x, y, and z. And if you had phi going out here, then this is rho here, okay? And this is phi. Okay. And this would be the x and the y components of that. All right, next page. Oh, I forgot. And then if you're going to go the other direction, rho is going to equal, whoops, rho is going to be the square root of x squared plus y squared. Phi is going to be equal to, I did it again. Keep on writing theta. Is equal to tangent inverse of y over x, and then z is equal to z again. And then the last one would be you do the same kind of thing with the spherical system. So you have a vector, and then you have ax plus ay plus az. So this is your rectangular system. And then you'd say I'd want to find the a rho, transform it into the spherical system. And then spherical is rho, theta, and phi. And then you would have your rectangular top. No, it's not rho, dang it. Sorry. And spherical, where r theta, r. So this would be ar. And likewise, if you wanted a theta, it would be a dot a theta, and a phi would be equal to a dot a phi. And again, you would do a very similar procedure. You got a x dotted with a r. Whoops. You would just basically do each component, a dot product of each component. So you got ax dotted with ar plus ay dotted with ar, and then plus az AZ dotted with AR. And if you wanted to find the other components, you just carry out the same procedure again, and this ends up being AX. And you look at table, the next table, I think it's 1.2, and you find that AX dot AR is equal to sine of theta cosine of phi plus AY, which is AY is going to be sine theta sine phi, and then we have plus AZ cosine of phi. And again, I got all these values by looking up these values from table 1.2. And again, they present if you want to transform the variables. If you're given one point in one system to another point in another system, it would be P cosine of phi, rho sine of phi. Oops, I'm writing the wrong ones. I went back to cylindrical again. So if you had 2 points, say, or if you had a point in rectangular, or say, in this case, a point in spherical, and you wanted to convert it to a point in rectangular coordinates, then you'd use these formulas. R sine theta cosine phi, R sine theta sine phi, and then R cosine theta. And then likewise, if you wanted to go the other direction from a point in space in the rectangular to spherical, then you'd go R is equal to the square root of x squared plus y squared plus z squared. And theta is going to be equal to z, or the cosine inverse 1. The inverse cosine of z over x. I did it again. Of x squared plus y squared plus z squares. And then if you, let's see, something's not right here. And then phi, okay, I was right. Just want to double check. Phi is going to be equal to the tan inverse 1 of y over x, the same thing. So again, this side here is if you want to do from a point in spherical space to get the point in x space, and this is if you want to get a point in x cylindrical to a point in spherical. And then all this stuff up here is if you have a vector in rectangular coordinates and you want to convert it into spherical coordinates, and then you have to carry out this procedure on each of its components. So you do each one in step. And so this is just the AR component that I calculated right here. And so that concludes chapter 1 of the basic information that's in there. One other thing that I forgot, and so we're not quite done, is the cross product of the component unit vectors. So I wrote here the rectangular, cylindrical, and spherical. And how I remember all this is I write down what the point is for rectangulars, x, y, z, and a point in rectangulars, rho, phi, z, and a point in spherical is r, theta, phi. And you can write down just straight off from their coordinates that you just remembered. the unit vector of AX crossed AY is equal to AZ. And then to get the other ones, you just kind of, as I've drawn an arrow here, kind of move everything down one and then loop around the last one. So we move the AY over, the AZ over, so we got AY cross AZ, and then we have AX looping around is equal to AX, and then likewise we do it one more time. We've got AZ cross AY is equal to AX is equal to AY. And so that gives you the three cross products for the rectangular and cylindrical. And similarly, you can do the same thing in cylindrical. You got A row from the row, A phi, AZ, and that's the cross product relationship. And then you just move everything down one. So the row goes down one, the Z goes down one, and you wrap around the phi, and there it is. And you just repeat it one more time. And you got AZ cross A row equals A phi. And you just repeat the same procedure for spherical. You got AR, A theta equals A phi. Then wrap it around. You got A theta, A phi equals AR, then A theta, A phi cross AR equals theta. And so there's all your relationships for the cross product of unit vectors in the three coordinate systems. One thing I forgot to mention before is that a cross, so not equals, but a cross B is equal to minus B cross A. They don't commute. Just like in the dot product, A dot B is equal to B dot A, but it's not the case in the cross product. So if you have something like AZ cross AY, it's not one of our listed options, but it is basically the flip-flop of this one here. If you just put Z in front of the Y, and so all you have to do is put a minus sign in front of the A. And likewise, if you were doing something in, say, cylindrical coordinates where you had AR cross A theta, it's not one of our options, but it is the opposite of this one if you reverse the two. And so you just put a minus sign in front of it. And since there's a sine theta term in the the cross product, and the sine of 90 is 1, and the sine of 0 is 0. Just remember that. Anytime you have two vectors or two unit vectors that are in the same direction, you're going to have the cross product be 0. And so I've written it out here.